screen, and then I will eventually write on the slide. So please tell me if you can see something.
Yes, I can see very well.
Okay, great. So, well, first some general comments to begin. So this talk will be very elementary. So perhaps it has something to do with the WKB part of the conference, but I will not really be talking about WKB. So what we will be interested in is the problem of reconstruction of linear ordinary differential equations or systems of linear ordinary differential equations in the complex domain from their monodromy data or Stokes data. So I'll be talking about the inverse monodromy map. This is, of course, a very old problem studied by Riemann, Schwarz, Poincaré, and others after them. So the simplest model cases of this reconstruction problem correspond to ODEs for classical special functions like hypergeometric, Bessel, Airy. And well, perhaps the simplest example is the hypergeometric equation, which is the canonical form of a second order ODE with 3 regular singularities. Now, from the very beginning, I would like to emphasize one important point, is that reconstructing an ordinary differential equation is actually an easier problem than solving this equation. So, for example, if you are talking about hypergeometric equation, all that we need to know to reconstruct it, well, we need to know the Riemann scheme, right? The local monodromy exponents. But in principle, we don't need to know anything about the actual solution of this equation. Now, if you want to try to go beyond this classical ODEs, then it turns out that increasing their order or increasing the number of singular points or making the singularities more irregular complicates this reconstruction task enormously. Well, first of all, you start to see the difference between the case of scalar equations and linear systems. And more importantly, you have now accessory parameter problem. So in the differential equation, you will have a certain number of parameters with a complicated, highly non-trivial dependence on monodromy. So next to simplest model cases where you can encounter this type of phenomena, they correspond to Hoyne's equation and its degenerations when we are talking about scalar second order ODEs. So the degenerations include several familiar examples like Mathieu equation or cubic and quartic quantum oscillator. And in the case of rank 2 linear systems, so this first non-trivial situations of the inverse of the explicit construction of inverse monodromy map, they are directly related to solving Painlevé equations. So I'm going to explain this construction, focusing on a specific example. So in the case of scalar ODEs, my main example will be Mathieu equation. And in the case of linear systems, I will be dealing with the most degenerate Painlevé 3 equation. Okay, so let me start with Mathieu, which is an equation for, which is a Schrödinger equation for cosine potential. So one can think about a particle moving in a periodic potential, and from the point of view of theory of ODEs in the complex domain, it makes sense to make this change of variable here and to make our potential rational. So now we see that we have two irregular singular points. One is at 0, one is at infinity. And in a sense, the equation that we get is a minimal non-trivial deformation of the Bessel equation. So if we remove either this z-1 term or this z-3 term from the potential, then we get something which is reducible to Bessel. Now, in this equation, so the parameter which corresponds to the energy, or to this parameter epsilon here, so this is called accessory parameter, because it is not fixed by local monodromy data. Okay, and so our problem will be essentially to have a practical way to compute this parameter in terms of monodromy. Right, so I told you about Mathieu, but actually we have a whole degeneration scheme of this second order ODEs. So Mathieu is located in this corner of the diagram. So I'm not going to explain the precise meaning of this picture. It suffices to say that so the holes on the surfaces, they correspond to singularities of the equation, and so the number of cusps is essentially the order of the pole of this quadratic differential -2. Okay, but we have here the usual Hoyne for 4 regular singularities. We have cubic oscillator, quartic oscillator here, and so on. Well, so now what should we do? So since our potential is a periodic function, we may try to find, to look for joint eigenfunctions of this Hamiltonian and translation operator. So we make this Floquet substitution, and then we readily obtain a 3-term recurrence relation for the coefficients of this Fourier series. And this recurrence relation, it has, of course, a non-trivial solution only if the matrix, the infinite matrix representing this, the corresponding linear system, has vanishing determinant. So this is the so-called Hill determinant. So the denominators that you have here, well, they are introduced just in order to make the determinant well defined. And let me note that so the parameter nu, so this Floquet exponent or quasi-momentum in physical terms, this is nothing but monodromy of our function psi. So this is the monodromy. So if you look at our previous picture, where we have two singularities at 0 and infinity, so nu is the monodromy exponent along this cycle. Okay. And so now if you write the equation delta of nu equal to 0, so this is an equation relating monodromy and accessory parameter, the energy. So in principle, it can be used in order to solve the direct and inverse monodromy problem for Mathieu. One thing that helps in this task is the following remarkable formula. So this is something very classical in Whittaker-Watson. So the Hill determinant evaluated for an arbitrary monodromy exponent nu is equal to the same determinant at exponent 0 plus a term which contains the whole dependence on monodromy. And so we can rewrite the equation determining the exponent nu in terms of accessory parameter E in this way. Okay, so we have this, and the rest is the function of only energy. So at least formally, we have solved completely the direct monodromy problem. Now, what should we do if we want to invert this relation? Yeah, before I explain this, so there is a remark here. So even though this is written for Mathieu, in principle, this procedure works for an arbitrary periodic potential or rational potential. So there is absolutely no problem in obtaining an analog of this relation. Now, for inverting this identity, well, it is more delicate, but well, if we manipulate this recurrence relation for the coefficients of our Fourier series, we can transform it into the following continued fraction equation. So there are some assumptions to be made here. One assumption which is which can in principle be relaxed, just we have to modify the computation a little bit, is that the monodromy has to be non-resonant. So the monodromy exponent nu has to be not non-integer. And also the coupling constant, so this the coefficient in front of the periodic potential has to be sufficiently small. And well, under this assumption, the equation that we have here can be solved in a straightforward way, iteratively, by making this ansatz. So basically, we substitute the accessory parameter in the form of a power series in this time variable, and then we just have to truncate our continued fractions at the desired order of precision. And then, well, if you compute, this can be easily implemented in Mathematica, and computing this series order by order, we get well, this expansion, which you can also find in many classical textbooks on special functions. So actually, all what I'm explaining now is very old, very classical. Basically, it is 19th century mathematics. Now, so this accessory parameter function, well, so we have two ways to compute it. One is based on Hill determinant. Another one is based on this continued fractions. From continued fractions, we get a convergent series, but the radius of convergence of the series is actually finite. So this converges for sufficiently small times, but later the series develops branch points. And the coefficients of the series, as you can see, they have poles precisely for this resonant values of monodromy. So for new integers, the coefficients they have poles. In the resonant case, the continued fraction method can still be adopted, but well, the answer will have a rather different form. The expansion is reorganized. So in particular, instead of having a series in powers of r to the fourth, you will have a series in powers of r squared. Okay, so this is a summary for Mathieu. So the direct monodromy problem is solved using Hill's determinant. So this is something which you could, in principle, try to do with WKB, but in the case of Mathieu, this is not even needed. We can obtain an exact answer at all order in h bar, which is put to 1 here, if we are interested in the series with respect to time. Now, for the inverse monodromy problem, well, we need to use continued fractions, and both of these computations, they actually remain completely valid if we look for on the equations from the upper part of this degeneration diagram. So Hoyne, confluent Hoyne, and so on, up to Mathieu. But it doesn't work for this cubic, quartic, cubic and quartic oscillator. Good. And it turns out to be convenient to introduce, instead of this accessory parameter function that we have, its integrated version, which is, so basically this E is the logarithmic derivative of another function which I call f. And there is a nowadays well-known conjecture that this f is the quasi-classical Virasoro conformal block. I don't actually know what is the right reference to put here. I think the earliest reference is a paper of 1986 by Zamolodchikov, but in this paper it is done for Hoyne equation. But for Mathieu, the procedure is, I mean, the extension or the generation of this result to Mathieu is really straightforward. And another thing which is unclear to me is, well, the status of well, existence of this quasi-classical Virasoro conformal blocks. Everybody believes that Virasoro conformal blocks, they admit quasi-classical limit. There have been claims, many claims in the literature to prove this, but still the mathematical status of these claims is not so clear to me. Fine. So now let me pass to Painlevé equations. So the nonlinear relative of Mathieu equation is the so-called Painlevé 3-3, or sometimes we use the notation Painlevé 3 D8 equation. So it usually appears in applications in the form of this radial Saint Gordon, or well, there is also this canonical form, which is how Painlevé 3 appeared in the classical works of Painlevé and his students at the beginning of the 20th century. But actually, the explicit form of these equations will not be so important for us. What is important is their geometric content. So let me recall once again that Painlevé functions, they solve the inverse monodromy problem for systems of linear ODEs with prescribed monodromy and prescribed singularity structure. And this Painlevé 3-3 corresponds to linear systems of this form. So you see we have two irregular singularities at 0 and at infinity. And the corresponding coefficients are non-diagonalizable. Now, the rest of what is written here is just a parametrization of our linear system. So this P, Q, and T are just some convenient letters, some convenient coordinates on the moduli space of such systems. Now, we ask the same question as we had for in the case of Mathieu. So this system has is characterized by a certain amount of monodromy data, Stokes matrices, connection matrices, and so on. And the question is, for a given monodromy data, can we find P, Q, and T? And it turns out that if, in addition to monodromy, we no, let me say it differently. If we fix the monodromy and we will try to vary this T variable, then the corresponding parameters P and Q, they become functions of monodromy and this time, which automatically satisfy this system of first order nonlinear equation, which is equivalent to Painlevé 3. Okay. In other words, if we manage to construct somehow for a given monodromy and a given time variable, so this, if we manage to calculate this P and Q, then automatically we will have the general solution of our Painlevé 3 equation. The answer is actually expressed in the nicest way in terms of the tau function, which was mentioned in the talk by Kohei Iwaki and in the discussion after the previous talk. So here the tau function has the following simple definition. So basically, what is written here is the non-autonomous Hamiltonian of this system of ODEs. And again, so I show you the degeneration scheme, which has exactly the same form as in the case of Hoyne equations. So we have Painlevé 3 in this corner. So these cusps correspond to the non-diagonalizable coefficients of the most singular terms. So these four regular singularities would correspond to Painlevé 6 and so on. Yes, and actually I haven't said it for Hoyne equation, but here it's kind of important. So this degeneration diagram is a degeneration diagram for linear systems, but some classes of this linear system, they actually lead to the same Painlevé equations. So for example, linear system here, which has two regular singularities and one irregular singularity of Poincaré rank 1 with non-diagonalizable highest order contribution, is actually solved. So the reconstruction problem is solved with the same Painlevé 3 functions as for the linear system having two generic irregular singularities of Poincare rank 1. So now, how can we attack this reconstruction problem? So the inverse monodromy problem in this case. So without going into technical details, I will just try to explain you the main steps. So the first step is to convert the linear system of ODEs that we have here into a Riemann-Hilbert problem on a circle. So the idea is very simple. So in the complex plane, we have so this irregular singular point at 0, the other irregular singular point at infinity. And now let us introduce here a fictitious circle, C. One can take it of any radius in principle. Because, well, we have these irregular singularities, our fundamental solution, phi, will have a certain monodromy along this circle, right? So now we can try to model the behavior of the actual fundamental solution at infinity and at 0 using two auxiliary linear systems which we can actually solve. So if we compare our linear system with Mathieu equation from before, so it works in the same way. If we forget about this term, then the corresponding system can be solved in Bessel functions. The same applies if we delete from our system this term. So now we can, so using these auxiliary solutions, which are supposed to mimic the behavior of the true solution at irregular singularities, and also reproduce the monodromy of the actual fundamental solution along this circle. So we can introduce the following functions. So one is phi times psi minus minus 1. Another one is phi times psi plus 2 minus 1, where this psi minus and psi plus, they are solutions of these auxiliary simpler systems outside, having Fuchsian singularity, one Fuchsian singularity and one irregular singularity. So one is at 0, another one at infinity. Now, you see, if from these two auxiliary solutions we cook up a matrix that I denote psi bar of z, then so this will be the expression of this psi bar outside of our circle. This will be its expression inside the circle. So the resulting matrix will be perfectly analytic inside and outside the circle, but it will have jump here. And so the jump matrix will be given essentially by the ratio of these two auxiliary solvable Riemann-Hilbert problems. And so if we manage to factorize the jump matrix in the other way, like this, So we get for free our fundamental solution. But the point I want to make here is that so we have converted our original system of linear ODEs into a Riemann-Hilbert problem with a set on a single circle with a jump matrix which is perfectly analytic in a certain tubular neighborhood of C. And now comes the definition. So given such a Riemann-Hilbert problem, the proposal is to define the tau function, which is a functional on the space of this possible jumps J, as a certain Fredholm determinant. So, so we have. So let me explain the notation here. So H is the space of functions on our circle times C2, which is the rank of our linear system. So this H decomposes, of course, into a direct sum of spaces of functions that can be continued analytically inside and outside C. So this is what the indices plus and minus refer to. And so in principle, the definition of tau requires only the knowledge of the jump matrix. But now, if in addition we have one of these factorizations, we can rewrite the corresponding Fredholm determinant in this way. So what we have here are essentially some integral operators acting on vector valued functions on the circle, which have this integrable form. So this is the kernel. Yeah, but the point to stress here is that in the case we are interested in, so this psi plus and psi minus entering the Fredholm determinant, they are completely explicit. They are given in terms of Bessel functions, essentially. Now, why is this definition good? Well, because there is a remarkable theorem due to Widom, which states the following. So suppose that our jump matrix depends on some extra parameter t. So for us, t will be the isomonodromic time, but in principle, it can be anything. So it can be a local monodromy exponent or any other monodromy parameter. So if our jump matrix depends smoothly on this extra parameter, then we have this variational formula. And the proof of this variational formula is actually rather elementary. So it basically uses the fact that these operators, let's call them P and Q, so we can find explicit inverses of these operators, and therefore, so in order to compute the derivative of something like determinant of PQ, we just have to take the trace of something like P minus 1 times the derivative of P plus the derivative of Q times Q inverse. And since we know P and the inverses of P and Q in terms of these factorizations, well, we can actually end up with this contour integral representation for the derivatives. And this is valid for arbitrary jump matrix. Now, if our Riemann-Hilbert problem comes from the isomonodromy, like in this example that I am focusing on, Painlevé 3, so then remember that, so for example, this matrix here, so this is essentially the fundamental matrix solution of our linear system. Therefore, so this fundamental matrix, it satisfies certain linear differential equations in Z, as well as in time variable. And so these linear differential equations allow you to reduce the computation of this contour integral to residues, basically. And what you end up when you compute all of the residues here, well, you end up essentially with this formula, which is the original definition of the isomonodromic tau function by Jimbo, Miwa, and Ueno. So there is some elementary correction, but it is very easy to calculate. Now, in a more general setting, so suppose that we have a system with two irregular singularities at 0 and infinity. So in a more general setting, this Widdom's variational formula allows you to prove that the tau function of this system is equal to the product of isomonodromic tau functions associated to these two simpler systems, and a certain Fredholm determinant, which is nothing but so this determinant that I have here, which is again expressed in terms of solutions of these auxiliary linear systems. Now, if the auxiliary linear systems are too complicated, well, then it might be difficult or even impossible to proceed. However, in the case we are interested in, so the auxiliary systems are, so let me just recall you once again, so they correspond to Bessel functions. So this gives you an kind of analog of the Hill's determinant, but which solves the inverse problem. So you give me the monodromy of the linear system that I have just shown. Then, well, I have to plug this monodromy into Fredholm determinant, compute the tau function, and from the tau function, I can compute P and Q or any other coordinate you might be interested in. It seems there is a question. Okay. It's the slides. Now, in addition to this explicit Fredholm determinant representation, one can actually obtain yet a different way to compute this isomonodromic tau function. So for that, all you have to do is to expand this determinant into a sum of principal minors in the basis of Fourier modes of this function, vector valued functions that live on this auxiliary circle. And this gives a completely explicit series representation. So I will show you the formulas. Well, of course, it is not really important to go deep into the structure, just to convince you that the results that we obtain are fairly explicit. So this is the first Fredholm determinant representation, and this is the series representation. So when you compute it, the final result is that the tau function is given by a Fourier transform of a certain function that I call z, which is given by a double sum over Young diagrams, and which has many incarnations. It has algebraic definition as the C equal to 1 Virasoro conformal block. It has a geometric definition as a generating function of volumes of instanton moduli spaces. Anyhow, so we have this explicit representation, explicit solution of the inverse monodromy problem for the class of linear systems I have mentioned. So the advantage of this representation as compared to the solution of the inverse monodromy problem for Mathieu is that here we are actually dealing with convergent series in the whole complex plane. So if I forgot to explain the meaning of different parameters. So eta and sigma here are two coordinates on the space of monodromy data. So sigma expectedly is the trace of monodromy in the intermediate channel. So it is the trace of monodromy along the circle. And eta is a kind of dual coordinate. So it's Darboux conjugate to sigma with respect to the natural Poisson bracket on M. Now, so perhaps you have already forgot, but so the series for Mathieu accessory parameter that we had before had a rather similar structure, rather similar to the series expansion of this conformal block function z. So let me go back and try to find it. So so we have this expansion here. So you see that this is the analog of the time isomonodromic time t. Again, we have the coefficients of the series which have poles at resonant monodromy. So it might be natural to ask, well, the notation already suggested. So is there any relation between the conformal block Z and integrated Mathieu accessory parameter F? So this is what I'm going to explain next. I think I have to skip the conformal block part. So so let me explain the relation that we have between Painlevé 3 and Mathieu. So reconsider the linear system associated to our Painlevé equation. Of course, we can convert this into a linear scalar ODE of the second order by considering any component of the fundamental matrix solution. But when we do that, it is rather obvious that in addition to original irregular singular points z equal to 0 and infinity, we will have extra apparent singularities. So this is because So essentially, all you have to do is to write the 2-1 element of the matrix A of Z and check the form of the potential. So you see that we have this spurious pole, which appears because we have to differentiate the logarithm of this element. And so now if we somehow want to convert our Schrödinger equation into Mathieu equation, then we have to fuse this apparent singularity at Q with one of the irregular singular points. So we would like to send Q either to 0 or to infinity. Okay, so in other words, we are interested in zeros and poles of this Painlevé function Q of t. So indeed, so if we do a local analysis of solutions of Painlevé 3, then it is fairly easy to check that near any zero in the complex plane, well, the expansion of different ingredients of our potential. So this expansion has this form here, and therefore, if we indeed just send our time variable to a 0 or to a pole of Painlevé function, then we get exactly Mathieu potential. And so the dictionary between Painlevé 3 and Mathieu is as follows. So the position of 0 or a pole of this function corresponds to the Mathieu coupling constant, so to the coefficient in front of the cosine potential. And the accessory parameter, so the function that we are really interested in, is the logarithmic derivative of the tau function of Painlevé 3. Moreover, so it is not necessary to treat the cases of zeros and poles of Q separately, because well, Painlevé 3 has a certain Z2 symmetry, which so basically, if a function Q solves Painlevé 3, then T over Q solves it as well, and the corresponding tau function transforms in this way. So it means that, so if we have a 0 of Q, then even though the associated tau function is non-vanishing, the Backlund transformed tau function has a simple 0. And vice versa. If you have a pole of Q, then the associated tau function has 0, but the Backlund transformed tau function is regular at this point. Okay. And the monodromy data transform under this Backlund transformation in a fairly simple way. So basically, this transformation simply shifts the exponent sigma by 1/2. Okay. And so now we will try to use this this dictionary in order to obtain a precise relation between these functions that we have introduced, the accessory parameter in Mathieu and C equal to 1 conformal block. So for that, let me note that so this connection allows to introduce the coordinates on the space of Painlevé 3 initial conditions on the space of monodromy data in a slightly different way. So instead of using this monodromy parameter sigma and eta, well, we can take as local coordinates the position of a movable pole of Backlund transform solution or 0 of Q, and the first non-trivial coefficient in its expansion around this point. Now, it is fairly straightforward to compute the symplectic form that we have associated to Painlevé 3 using either this pair of coordinates or this pair of coordinates. So all one has to do is to substitute into this formula the asymptotics of the corresponding Painlevé functions near, let's say, critical point t equal to 0 or movable 0 or movable pole t equal to s. So if you do the computation, it turns out that this symplectic form, which is preserved, sigma and eta are just standard Darboux coordinates, but so this accessory parameter E and log of the position of a movable 0 of Q are also canonical coordinates. Therefore, we can cook up one form on the space of monodromy data, which is closed. And this F, is such that the accessory parameter is obtained by computing this logarithmic derivative. And on the other hand, the Darboux conjugate monodromy parameter is another derivative of this F with respect to sigma. So basically, what we are writing here is that so this function F is the generating function of the canonical transformation between these two pairs of coordinates. And recall once again that this is precisely the logarithmic derivative of Mathieu accessory parameter with respect to time. Now let us come back to Painlevé tau functions. So recall once again that so we have a relation to Mathieu when when either tau function of t or a Backlund transformed tau function has 0. Okay. So let us just write this equation using this Fourier transform formula that we had. So recall that we had the tau function given by a Fourier transform, of the C equal to 1 conformal block, Z to sigma plus n t. And so what we have to do, first of all, so the Backlund transformation of this tau function shifts the monodromy parameter by 1/2. And second, so we have checked before that this dual monodromy parameter is essentially the derivative of this generating function with respect to sigma. Okay, so now this this equation tau twiddle equal to 0 gives us a first of the equations relating F and Z. It is possible to obtain yet another relation. So I'm almost finishing now. So, so this other relation is now inhomogeneous. So basically, what it tells you, it computes a connection constant between the asymptotics of isomondromic tau function at critical point, so fixed singularity, and a movable pole, movable zero of the tau function. So this can be computed using a certain extension of this one form defining the tau function to the space just from the space of isomonodromic times to the space of monodromy data. And so this is basically what it gives you. And a remarkable thing is that so the two equations that I have shown you, so this one and this one, they actually determine Z in terms of F and vice versa. So if you know somehow the expansion, the series expansion of the quasi-classical conformal block, then you can compute the series expansion of the C equal to 1 conformal block and vice versa. Now, why is this interesting, in my opinion? It's because, well, it's because the lower part of this degeneration diagram that we had. So in the lower part of the degeneration diagram, we know from numerical experiments that the tau function still have a Fourier transform structure. So this formula, like this one, T sigma plus n, still holds true even for Painlevé 1, 2, and 4. However, we don't have a nice algebraic or geometric definition of the function G, of the function Z, sorry. So this is would be C equal to 1 conformal block, or maybe would be a topological recursion partition function. But on the other hand, so the function F, so this accessory parameter function, we can compute using WKB indeed, because F is essentially the inverted Bohr-Sommerfeld period. Okay, so the computation that I have explained you for Painlevé 3, it can be done in precisely the same way for the other Painlevé equations. And so in principle, so the equations of this type, they allow you to give an independent characterization of this Z in terms of accessory parameters. Right. So this is what I wanted to say, and yeah. So the content of my talk is resumed in the following picture. So we have started with Mathieu equation. So conjecturally, the inverse monodromy problem of this equation solved with quasi-classical conformal blocks. We have considered Painlevé equations. So here it is a theorem that the inverse monodromy, related inverse monodromy problem is solved in terms of C equal to 1 conformal blocks. Now the relation between Painlevé 3 and Mathieu, so this story about movable zeros and poles, can be transformed into a very concrete identities relating these two types of conformal blocks. And it turns out that these identities can be seen as a quasi-classical variant of the so-called Nakajima-Yoshioka blow-up relations. Yes, so so this is I think the time to stop. So thank you very much.
Thank you. Okay, are there any questions? Maybe I ask a quick question to start off with. I mean, can we think of this as there is one big space which is parameterizing these ordinary differential equations with apparent singularity, and you know that there is a special locus where this apparent singularity has gone to 0 or infinity,
sure,
and then a map from that to the monodromy data, and then you have two generating functions which have something to do with the geometry of this space and the map, right? I mean, one of them has to do with the monodromy where the apparent singularity is at infinity, and the other one is different. I mean, can both of these functions be viewed as describing the geometry of this kind of space? And is there any geometric reason for this blow-up relation between the two functions?
By the two functions, you mean still this f and z?
Yes, I mean like the Painlevé tau and then this f. Yeah.
Well, maybe York knows something about it, but I don't know any interpretation of this z as a generating function.
Right.
So the quasi-classical conformal block is definitely a generating function, indeed, between two convenient pairs of coordinates on this extended space. But for z, I don't know.
But what about log tau? I mean, z is, I mean, isn't the tau function a generating function for describing the constant, the isomonodromy locus inside this space of equations? No.
I don't have answer to this.
Okay, sorry, it was a stupid question then. Would anyone else like to ask a question?
Yeah, well, if I may sort of follow up on this point. I mean, well, what I know from the literature is that there is a relation between this the tau function and the generating function for the monodromy map. I had mentioned this in the previous discussion, so there's claims to this effect by Bertola Korotkin and by Nekrasov. So I was also wondering what the relation is between your results and this interpretation, or this relationship between tau function and generating function.
So what we knew even before Bertola and Korotkin was the following thing, but which somehow excludes isomonodromic time from the discussion. So if we have the isomonodromic tau function, let's take again this Painlevé 3. So one can study two asymptotic regimes. So one is t goes to 0, and another one is t goes to infinity. Now, the tau function, once again, if you don't have a preferred normalization, so the tau function is defined up to an overall constant, which may depend on monodromy data. And so the asymptotic behavior in these cases, so we have some, you have some asymptotics here, and you have some asymptotics which I unfortunately forgot. So there is some exponential term, there is some power of t, and so on. So you cannot fix these coefficients c and d separately. However, so the ratio of these coefficients is actually independent of the normalization of the tau function that you choose. And this ratio, so this is what I call a connection constant between these two critical points. And this is indeed, this turns out to be indeed a generating function of a canonical transformation on the space of monodromy data only. Okay, so there is no T in the story. So it's like a generating function. So in the case of Painlevé 6, it would be a generating function of a canonical transformation between two pairs of Fenhill-Nielsen coordinates. Now, to be honest, I don't.
One is actually for Kontrov, by the way. But anyway, there's not.
Yeah, but I don't quite understand. So probably Marco Bertola and Dima Korotkin do understand how to incorporate the time into the story. But I was always, well, I was staying at the space of monodromy data.
Okay, one more question actually. Can you do this in the case of the cubic oscillator? I mean, you said earlier there was some problem with this lower row.
Right. So what can we do with cubic oscillator is that we can, obviously, we don't have Hill determinant, we don't have continued fraction, but we have WKB. And so in principle, so what WKB computes for you is the Bohr-Sommerfeld period. So it's something like nu, which is a function of the energy, and then you can invert this relation. So basically inverting this relation gives you an analog of F for Painlevé 1. Now the analog of Z you obtain in a semi-experimental way. I mean the following. So you have your differential equation, you have the tau function, you have its leading asymptotics. So you can plug it into the equation and compute more and more corrections. And then what you discover by computing these corrections is this the very same structure. So you see that the tau function is again it has this Fourier transform form up to a constant, of course. Where well, now in this so this function Z, we don't even know if it is an actual function or it's just a formal asymptotic series, but it's sort of so this periodicity structure, it sort of emerges from the differential equation. But in contrast to Painlevé 3, 5, and 6, so you see, we don't have an independent algebraic or geometric definition of this.
Okay, but sigma and eta are Fock-Goncharov coordinates on the character variety here.
Yeah, exactly.
P is Painlevé time.
Yeah, so exactly. So in Painlevé 1, so you have this 5 rays, right, on which you have this Stokes matrices, and so these variables like sigma and eta, they are related, well, basically to Stokes multipliers in Painlevé 1. So indeed, these are something like Fock-Goncharov for Painlevé 1. And yeah, by the way, this connection problem that I mentioned before for Painlevé 3.3, for Painlevé 1, well, it's basically the same story. And so computing this normalization change, relative normalization of the tau function between different rays in the complex plane of the argument, it gives you this connection constants given by dialogues. So, by the way, I was wondering whether there is any relation between this connection constant and this tau BPS, which appeared in the talk by Kohei Iwaki. So I would be interested if anybody has a comment on that.
I think there are lots of discussions around this question, but I think nobody knows the answer. Well, we should listen to Jörg's talks first. But last time we all discussed this, I think nobody had a clear answer. Yeah, I mean, somehow Kohei would like to generalize his story to the coupled situation, and the simplest example is this Painlevé 1 example. But
yes, and in addition, in the in the work by Kohei, so he manages somehow to prove this Fourier transform structure in a way.
Mm-hmm.
So,
yes.
And in his setting, so this Z is the partition function of the topological recursion run on an elliptic curve, right?
Right. And then this identity in the middle of your screen now, that is, I mean,
this one?
Yes, that's not known, or it is known.
No, for Painlevé 1, I can write precisely the same identity. If you accept this ansatz, then once again, so what is written here is just this. So this is a statement that a certain tau function of Painlevé 1 is equal to 0.
Mm-hmm.
That's it. So this basically follows immediately from this ansatz. And the second identity, well, it is almost like this. So I can write. We actually have with Kohei this the analogs of this identities for P1. Mm-hmm. And indeed, we checked that well, the first terms of this asymptotic series, they match the topological recursion calculations. We have checked that we can compute that the series for Z is determined by the asymptotic series for the accessory parameter. But well, yeah.
Okay.
No. These identities you do have for all of Painlevé.
Well, that's very interesting. I never saw these before. If there are no further questions, we should thank Oleg again. Thank you very much.
Thank you. So I can stop sharing.
Yeah, I should stop the recording.